Let's now talk about the approach piezo procedure, which is the second step of the TSPL configuration, which is also called as reader sensitivity calibration in the TSPL configuration. Again, we open the drop-down menu, we go to the approach piezo sub-tab, and we can control only this specific step of the TSPL configuration. So during this procedure, the cantilever slowly approaches the surface by extending the piezo on the z-axis, and we can see that we have an extension from 2 to 19 micrometers with very small steps. So this procedure takes also some time, and that's why we want to have the cantilever not too far away from the surface when we start the TSPL configuration, because otherwise it will take quite some time. We can see now the cantilever is well focused and the surface is also in focus, so it will take maybe 30-40 seconds. We can see while I run it how long it takes. So around 20 seconds, I would say 15 when we're very close. But let's say if we're at 2 millimeters away from the surface, this procedure can take around 10 minutes. So maybe some time that we can save. So by extending the piezo, at some point the cantilever will reach the surface, and as you can see here we have an approach curve and a retract curve. During the approach we extend the piezo until we find the surface in this point here, and then we start the retract curve, which will allow us to identify the adhesion length and the tip height estimate, as well as the sensitivity. So the millivolt that we need to apply to have a nanometer response in the reader. So to have and to understand a little bit more in detail this approach curve, we can either go to the user manual, which is quite well explained, or also use this image that I prepared for this step of the TSPL configuration. So we said that during the approach curve we are slowly approaching the surface. Then at some point the tip will touch the surface. We're in point 2, and at some point we will try to move the tip further down, but the sensor will realize that we actually found the surface. So we have a small deflection of the cantilever, and after we have detected the surface and we know that we have found the surface, we will do a retract curve. So we have an approach turnaround. And during this initial turnaround procedure, you see during step 5, the tip is stuck onto the surface because the adhesive forces. So for some time it will be stuck there until it snaps out. And during this snapping out step, we have a large, I'd say quite rather than large, we have a steep change in the reader signal. So this allows us to identify the adhesion length, which is this length here pretty much. So in this case we can see it's around 20 nanometers, and the adhesion length of the tip is a very important value because it helps us identifying the quality of the tip, in particular the sharpness of the tip. Let's go back to our NanoFrazor software. We see that we have these two values, the adhesion length, which can be approximated to the diameter of the tip, and the tip height estimate. So while one value gives us information about the sharpness, the other value, the tip height, gives us information about the length of the tip. We usually expect tips that are shorter than 1 micron, can be a little bit longer than that, but in general looking at the tip height estimate, we're able to understand what's happening to our tip, because while doing thermal scanning probe lithography, we can pick up some contaminations, for example, so the tip can grow longer in height, or we can also damage the tip because we're still removing quite a lot of material, and we're also doing a reading process, which is a contact process, so the tip can be damaged, and in that case we will reduce our tip height estimate. So looking at the history of the tip height and the adhesion length, we can see what happens to our tip while we use the nanofraser. So in this case, we can see the three approaches that we did while using the tool, and every time we do an approach, so I can move a little bit and run another approach, another data point is going to be added to this curve. Now these data are not that helpful for us to understand what's going on with our tip, because nothing is really going on at the moment. But usually if we pattern and we see that the patterning quality decreases, or we struggle to pattern the way we want, maybe it is because we pick up some contaminations, or the tip got blunt and the conditions of our system changed. And this phenomena can be detected or can be understood a little bit better if we have a look at the adhesion length or the tip height estimate. Another important thing that I would like to mention about the adhesion length is that since it's directly related to the sharpness of our tip, we need to have a good look at this value when we want to do a TSPL process. Because if we want to pattern at high resolution, which means features maybe below 50 nanometers or 60 nanometers, we need to have sharp tips. And in general, we say that if we want to pattern at high resolution, a recommended value for the tip adhesion length is below 40 nanometers, while if the adhesion length is roughly below 100 nanometers, we are able to pattern pretty much all the non-high resolution features. So in terms of usage of the cantilever, this is a very important detail that we need to take into account to not waste tips, and also to have achieved the best resolution and the best patterning without wasting too much time with tips that maybe are not really suitable for this specific patterning at high resolution. Another important information that we can get from this approach curve is the resting distance of the cantilever. How do we get it? Well, we said that when we have to find the surface, the piezo will slowly extend in the approach part, and then it will retract. So after it extends, in this case for around 11.756 micrometers, then it will have to retract to its original position, to its equilibrium position. And how long was the displacement of this retract procedure? It's going to be exactly 11.755 micrometers, or 756. So at this moment, we know that the cantilever is approximately 11.75 micrometers away from the surface. So when using the nanofraser, this is also an important information, because it's quite safe to move around. So you can see I'm doing a step of 50 by 50, but also I can move more than that, steps of 200, 300 in general, unless we have very big features or a sample with a very large slope. It's safe to move around without lifting much the cantilever, but it's always good in case we don't know exactly much about our surface or we want to just be safe and avoid any damage of the tip. We can lift the cantilever by 100 microns and move around more safely, maybe by larger distances. Say you want to move by 300, now it's a bit more safer to do it when we're farther away from the surface. So at this moment we know that after lifting by 100 microns we're around 100 microns plus 11.7 microns away from the surface. So if I want to do a new approach procedure, I can go down, say by 90, should be safe, and then I can run another approach. When we run the approach procedure, you see that we have also this relative perform location. In this case, we can choose whenever we are writing a field. In this case, it's not really meaningful, but we will see when doing TSPL or doing a reading process that we have always this specific view in the session. So let's say we go to the warm-up and we import a geometry. If we open this specific geometry, we see this view with a blue area, which is the scan region, the yellow area, the read region, which is a whole area into which we're going to move with our cantilever. And by choosing the relative perform location, we will tell the nanophraser where we want to do the approach in our layout, in our design. So in this case, if we press here, we will do the approach here, and it's also mentioned by the nanophraser software. So let's say change it and I put it in the center of our patterning area. You'll see that the approach position is marked by this small indicator. So to wrap it up, the approach piezo is a very important curve, probably the most important curve that we have to look when doing TSPL and when we use a nanophraser. It gives us information about the tip quality, about its sharpness, about the tip height, which can be important to understand contamination or blunting phenomena that happen when using the nanophraser. It can also give us information about how far we are from the surface, so the resting distance of the cantilever, and also we can choose whenever we do an approach where we do it, and if we want to play around with the settings of the steps, that's also possible, even though it's not often done by the nanophraser users. From the history, you can also have a better understanding of how the tip evolves during time, which is also very precious and useful information.